the epidemics will stop us to meet in person. So today we have Urmila Mahadev join us, and I'm really glad that we could have her to give a presentation here. She is currently an assistant professor at the Department of Computing and Mathematical Sciences at California Institute of Technology. She completed her PhD at Berkeley, also in California, not too long ago in 2018. Then stayed for a postdoc at Berkeley before joining Microsoft Research New England as a visiting researcher, and then the Simons Institute of Theoretical Computing as a research fellow in 2019-2020, before joining us at Caltech. And during her PhD already, she solved a major problem in quantum computing. It's a result that made quite some noise in the quantum computing world. And to have achieved a result like this during a PhD is quite outstanding. It needs a lot of determination, I think, to tackle a fundamental problem like this that she will tell us more about today. And these questions, or these kind of questions, are far from just being academic. So quantum computers really have the potential to offer exponential speedups on a host of problems, from modeling the behavior of black holes to simulating large protein foldups. So all problems where the computational power is a key limiting factor at the moment. Her results have been called one of the most outstanding ideas to have emerged at the interface of quantum computing and theoretical computer science in recent years. And also using a radically new approach, which is to use classical cryptography in the quantum realm. So with that, Urmila, I'm very much looking forward to your talk. Welcome.
Okay, thanks so much for the very kind introduction, Franca. And also thank you for inviting me. I'm very happy to be here. So as Franca said, this talk will be on a topic called classical verification of quantum computations. Just to check before I get started, can everyone see my screen okay? It's you should be seeing just the first slide.
Yep, we can see your screen.
Okay, so this topic lies in cryptography, complexity theory, and quantum computing. And I'm going to try to keep it at a really high level and just give you the necessary details and not do a thorough introduction to any of those topics. But my goal is that all of you follow the entire talk. So to help me with that, I would really encourage you to ask as many questions as you like during this talk. It's quite short, but I do want to get into the actual ideas behind these results. So that's my goal, to give you some sense of the high-level ideas. So let's get started, and I'll start by defining this question. What does it mean to classically verify a quantum computer? Here's how to picture it. You have an experimentalist, and we consider her our classical being. And I'd say she's classical because her computing power is limited by, let's say, a standard laptop. And we consider those classical devices because they're not using quantum mechanics. This experimentalist has access to a quantum computer. The quantum computer can run quantum computations, but the goal of the experimentalist is to verify that this quantum computer is actually performing a quantum computation correctly. So what the experimentalist does is she picks a quantum circuit of her choice, and she asks the quantum computer to perform the quantum circuit. And then let's assume that the output to the quantum circuit is just a bit. It's either 0 or 1, so it's a classical output. The quantum computer will get back to the experimentalist and will report the output is 0. The goal of the experimentalist is to verify that this reported output is correct in the sense that it's consistent with our theory of how quantum computers should behave. So we have a mathematical theory about what a quantum circuit looks like and what it means for this quantum computer to apply the circuit. We want to check that the output is consistent with our theory. So when you see a model like this, maybe the first thing you think is, well, why not the scientific method? This is what we do in similar settings, in which case the experimentalist would just compute the output. Like I said, we have a theory of how things should behave. And then she would just check that the output that the quantum computer reports is consistent with her prediction. The problem with this is that the scientific method falls apart in the context of quantum computations. And that's because quantum computations are exponentially complex, which rules out the possibility of an experimentalist, of a classical experimentalist, even writing down the state of a quantum machine, let alone performing in an actual quantum computation. So let me just give you a little bit of detail about what quantum computers look like so you can understand why this exponential complexity is such a huge hurdle. So if I take a quantum state on n qubits, it requires 2 to the n parameters to describe. This is the exponential complexity that I'm talking about. And here's what a quantum state looks like. So on n qubits, a quantum state is a superposition over all 2 to the n bit strings of length n. And each different bit string has a corresponding amplitude. In this picture, the amplitude is alpha x. And so you can write the state as a superposition, or you can write it as this vector, which is a 2 to the n dimensional complex vector. And when I write it like this, now you should be able to see that this experimentalist can't even write down an n qubit quantum state, because to write down that state, she'd have to write down these 2 to the n different alpha parameters, these amplitudes. So she can't even write down the state, which immediately rules out the possibility of her applying a quantum circuit. Because if she can't write down the state, then of course she can't manipulate these states as part of the circuit. So this is the first huge hurdle, that quantum states are exponentially complex, which rules out the scientific method, which means when we have access to only a classical computing device, we cannot predict the outcomes of a quantum computer. But it gets even worse, because not only are quantum states exponentially complex, classical access to quantum systems is extremely limited. So if we wanted to classically access a quantum system, the way to do it is measurement. And if I measure this quantum state, what happens is it collapses to one of the different x's, so one of these different bit strings, there are 2 to the n of them, and it collapses to x with probability corresponding to the amplitude. There is a theorem in quantum information theory called Hulevo's theorem, which states that a classical measurement of a quantum system can reveal at most n bits of the system. But what I just said was that the quantum state requires 2 to the n parameters to describe, but somehow when we classically access this quantum system, when we measure it, we lose most of that information, and we can only extract n bits. So putting this together, what I'm saying is that quantum computers are not only exponentially complex, but they're also exponentially private. And these two properties together is what makes the question of classically testing quantum computers so difficult. If quantum computers are so complex and our access to them is so limited, how can we possibly be sure they're behaving correctly? So I'm going to get into the how to test them in just 1 second, but before that, let me try to motivate this question from a few different angles. Hopefully you can already see the importance of it, because I'm sure many of you have heard about quantum computers, and given that our current computing power is limited to classical devices, it's quite important that even with limited computing power, we should be able to understand how quantum computers work. But I can motivate it more concretely from several different angles. The first is philosophical. So when we have a quantum computer, it's going to be operating on, let's say, n qubits. So at some point, it's going to reach this high complexity regime where the state it's working with is exponentially complex. And before, we could never quite test this high complexity regime because of its exponential complexity. But what this question is asking is there a way of testing quantum mechanics in a high complexity regime? So is there a way, once quantum computers reach this exponential complexity, to actually test that our theories are correct in this regime? So that's a philosophical question. It's asking whether we can test the correctness of quantum mechanics in a high complexity regime. The next is practical. So I'm not sure if you have heard, but recently there's been a lot of news about upcoming quantum devices. Currently, they're quite small. They only have about 50 to 100 noisy qubits. So these qubits aren't perfect and they have errors. And at this stage, it's unclear whether useful computations are possible on these devices because they're so small. But what is clear is that we're very close to the threshold. So once we go over this number, like let's say we get to around 100 noisy qubits, then the complexity is 2 to the 100. That's how long it takes to classically describe it. Once we reach that complexity, we cannot simulate these quantum devices, even though they're still small. We can't simulate them with classical supercomputers. So how can they be tested? Because right now, the quantum devices are small enough that we can still use a classical supercomputer, run it for a couple days, and test that our quantum computer is behaving as expected. But once we pass this threshold, when our classical supercomputers can't handle this task anymore, how can we check that this development of quantum computers is going correctly, that these are actually quantum devices? So that's a practical motivation. The final motivation comes from a field of theoretical computer science called complexity theory. And in complexity theory, one of the most well-studied questions is whether it's easier to test the output of a computation than to actually compute it. So in this case, is it easier to test the output of a quantum computer than to actually compute it? And that's exactly what I'm asking, because the classical experimentalist clearly can't compute it, but can she test it? Now, in the classical world, the answer to this question has been a resounding yes. It is much easier to test than to compute. And much of the progress was made by studying a different notion of proofs called interactive proofs. So in this picture, what I drew is a standard notion of proof. The experimentalist asks the quantum computer to do something. The quantum computer says, here, I did it. Here's a certificate that I did it. The experimentalist should be able to check the certificate or proof. We can extend the notion of a proof to an interactive proof in which interaction is allowed. So now the experimentalist will interact with the quantum computer over some number of rounds. And this is kind of like quizzing the quantum computer, maybe checking consistency of the answers, or maybe tricking the quantum computer by not telling him what the next question you're going to ask is. So the interaction gives the experimentalist extra power in testing the quantum computer. And in the classical world, it was shown that this extra power allows us to test a much larger class of computations than just the standard proof. And what I'll show here is that interactive proofs are actually very, very powerful in this setting. If the experimentalist can interact with a quantum computer, then she can actually verify the output to the quantum computation. And since interaction is such a huge part of this result, I'd like to give you just a simple example of why interaction is so powerful. So here's the example. Let's say there's a tree outside, and you tell me that you can count the number of leaves on the tree. And somehow I'm computationally limited. I don't have the time, or I don't have the ability to actually count the number of leaves on the tree, but I'd like to know the answer. So since you can do it, I can just ask you, well, what's the number of leaves on the tree? But now I have no guarantee that you're actually being honest, because what if you just, for some reason, you want to lie to me, you know that I'm using it for some purpose and you don't want me to have the answer. So is there some way that I can quiz you over some number of rounds, interact with you, and make sure that you actually know how to count the number of leaves on the tree? It turns out that there's a really cute solution to this. And the way I would do it is as follows. I'd ask you for the number of leaves on the tree. You tell me. Let's say you say 500. Then I blindfold you, so you can't see what's going on. I go outside and I pick a random number of leaves off the tree. Let's say I pick off 100 leaves. Then I bring you back. I ask you to look at the tree and tell me how many leaves are on the tree. You'll give me a number. What I check is that the difference between the original number and the new number you gave me is 100, exactly the number of leaves that I picked off the tree. Now, this is essentially checking that you have the ability to count the number of leaves on the tree. Because if you didn't, there's no way you could get the difference correctly, because you didn't see how many leaves I picked off the tree. So if you couldn't count the number of leaves on the tree, it all pretty much looks the same to you. So this is just a very rough, intuitive example of why interaction can make problems that seem hard, it can make them tractable to verify. Okay, so I'm going to get now into the question of interaction with verifying quantum computers. But before that, are there any questions on what I've said so far, just to make sure that people are following and I haven't said anything confusing?
So far, there are no questions in the chat. Edina, feel free to unmute yourself and ask.
Yeah, Urmila, thank you. So I wanted to ask, is there a lower bound here that we're shooting for the number of interactions in the rounds?
Yeah, in general, you want to have it efficient, so you want polynomial number. And then after you get something like that, then there's a lot of work on decreasing interaction. Like that's a big area of study. The reason people care about that is because eventually the goal is to get back to a standard notion of proofs. Like we want to see how far apart those two are. So yes, people care a lot. In the questions that I'm talking about, we just care about polynomial because we don't really know how to do interactive proofs. But once you know how, then people care about reducing it.
So there's no exponential speed up here in the quantum setting in the interaction proof system, is there?
Well, so exponential speedup comes up when you're talking about quantum algorithms for problems. And then you say, well, does a quantum algorithm have an exponential speedup over a classical algorithm? Here, I'm not talking about quantum algorithms for problems. I'm talking about verifying an output to an algorithm. So I'm not sure that there is a notion of exponential speedup unless you had one in mind, and you should tell me.
No, I didn't have one in mind. I was thinking whether we could basically do better than in a classical setting when we're doing an interactive proof. The number of bits, the number of rounds, can you get away with less than polynomial I was expecting?
Right, so this is a different question because there is no analogy in the classical setting. Here I'm saying, can a classical verifier verify a quantum computation? So there's no classical protocol for that. If you want, you could go back to classical interactive proofs and study whether quantum computation can help reduce the interaction. Maybe that's what you're asking. People are doing that. I don't know much about like what the status is on that field, but there's definite interest in that question.
Thank you very much.
Yeah. Okay, great, thank you. So let's move on into, now I told you why interaction is so powerful, and I'm going to be using interaction in the question of classically verifying quantum computers. So now we have this classical verifier, which I represented by a laptop in this picture because it's our classical computing power, and a quantum computer. So I replaced the experimentalist with this laptop. The goal is we want to classically verify quantum computers through interaction. So this laptop will interact with the quantum computer over some number of rounds. And at the end of the interaction, the laptop should be sure that the output to the quantum computation is correct. So this question was first asked by Daniel Gottesman in 2004. And the question was, can a classical computer verify the result of a quantum computation? And just to put a bit more terminology that I'll be using, in this setup, the classical computer is referred to as the verifier. The verifier wishes to verify the output of the quantum computation. The quantum computer is the prover. He's trying to prove that what he's telling you is actually correct. And the conditions are as follows. There's the completeness condition, which says that if the prover is being honest and reporting the correct output to the quantum computation, the verifier must accept the output as correct. Then there's the soundness condition, which says that if the prover is being dishonest and reporting the incorrect output, the verifier should reject with reasonably high probability. So that's what I want. I want an interactive proof in which the verifier accepts if the prover is correct, and the verifier rejects if the prover is incorrect. Okay, so the reason this question is so hard is what I told you earlier. This classical computer is so much weaker than the quantum computer. How can the classical computer possibly gain any leverage over the quantum computer in order to verify that the quantum computer is behaving correctly? And this is where cryptography comes in. So far, we've just talked about this quantum computer as this very powerful device. We have no idea what he's doing. It turns out that we can use classical cryptography to upper bound the power of a quantum machine. So what I'll use is this quantum machine. He's very powerful, but he's still only doing polynomial time quantum computers. He's doing efficient quantum computations. What I can use is I can use an assumption that an efficient quantum computer cannot break certain classical cryptographic problems. This is called quantum secure cryptography. It's classical cryptography that an efficient quantum computer cannot break. So I'll give you a concrete example, which is called learning with errors, and this is the most widely used assumption. Learning with errors, it's just if the cryptographic problem is as follows. You get a system of noisy linear equations. So if I just give you a system of linear equations, you know how to solve those. But if I take every equation and I perturb it by just a small amount of noise, it turns out that even a quantum computer cannot solve that noisy system of linear equations. And this is an assumption. And what that means is that due to all of our current research, we do not believe that quantum computers can solve this problem called learning with errors, but we haven't shown that they can't solve it. So that's why it's an assumption, because it's very hard to prove that one can't solve it, but we believe that quantum computers cannot solve it because of the extensive amount of research that has gone into attempting to develop quantum algorithms for this problem. So what I will rely on is the assumption that quantum computers cannot break this problem called learning with errors. And this is the most widely used assumption in quantum secure cryptography because it's the most well-studied one. People have tried really hard to come up with algorithms for quantum computers to solve learning with errors. So what I've said so far is our quantum computer is powerful, but he's not all powerful. We believe that there are problems that the quantum computer cannot solve. So what I've done so far is, well, the verifier and the prover were on very different levels. The verifier was very weak. The prover was very powerful. Now I've upper bounded the power of the prover by using this assumption, but I still have this inherent imbalance. The verifier is still much weaker than the prover. So how do I kind of prop up the verifier so he has a bit more power over the prover? So what I can use is something called a trapdoor. Okay, so when we use cryptographic assumptions, the way we use them is as follows. So here's a rough example. I would give the prover some function. Let's say it's a function which he can evaluate, but I say if he can invert this function, then I link it to the cryptographic assumption. I say if he can invert it, then he can break learning with errors. Therefore, I assume that the prover cannot invert it. This is called a one-way function. I assume that the prover can evaluate it, but it's hard for him to invert it. There is something called a trapdoor, where if someone else has access to this trapdoor, then that different party can invert the function using the trapdoor. So think of the trapdoor as a secret key, which allows the verifier to kind of unlock the function and invert it. But the prover doesn't get access to the trapdoor. So what the verifier will do is he'll generate a function along with a trapdoor. He'll send the function over to the prover. The prover will be able to evaluate but not invert, but the verifier will be able to invert by using the trapdoor. And so by allowing the classical machine access to this trapdoor, we somehow restore the balance between the verifier and the prover because I give the verifier the ability to do something that the quantum prover cannot do. So what I've said in this slide is that we started off with this huge power imbalance between the verifier and the prover. The way I'm addressing it is by first upper bounding the power of the prover, saying there are some things that even a quantum prover cannot do. He can't break this learning with errors assumption, and he can't invert a one-way function that's based on this assumption. Then I lift up the verifier by giving him access to this trapdoor, which allows him to compute something that even the quantum computer cannot do. And it turns out that just this is enough to allow a classical verifier to interactively verify the output to a quantum computation. And so for the rest of this talk, what I'll do is I'll tell you more about these functions. So I'll describe them concretely. I'll tell you how they work, how a quantum computer works with these functions, and how the verifier can use his trapdoor in order to force the quantum computer to behave correctly. So that's next. Before that, are there any questions before I get into the actual construction?
There are no questions in the chat at the moment, but if anyone has any questions, feel free to just unmute yourself and ask.
Thanks, Franca.
Can you summarize all the assumptions that are required for the assumption? So there's underlying this P is not equal to NP. There is the fact that quantum computer cannot solve linear equations with errors. Is there any other assumption?
No, it's just, so the P is not equal to NP. You can just say the assumption is learning with errors. And the assumption is learning with errors implies different assumptions because if certain things are true, then learning with errors will not be true. So let's just say our only assumption is that the quantum computer cannot break learning with errors.
All right, thank you.
Yeah. Okay, thanks for the question. Let's continue. So now I gave you this example of a one-way function, but in reality, I'll be using something slightly different. So let me define the actual functions that I'll be using. So I'll define the cryptography that I'll be using. Instead of a one-way function, I'll be using something called a trapdoor claw-free function pair. These were first defined by Goldwasser, Macaulay, and Rivest in 1984, and here's the definition. A trapdoor claw-free function pair is a pair of functions f0 and f1. They're injective and they have the same image. So both functions are injective and their images are exactly the same. The claw-free property says that it's computationally difficult to find a claw. A claw is a pair of pre-images which map to the same point. So this picture here kind of looks like a claw, and that's why it's called a claw. So let's say x0 and x1 map to the same point, meaning f0 of x0 equals y, and f1 of x1 equals y. This is called a claw. And the claw-free property says that it is hard to find a claw. So this is the same as before when I said it's hard to invert a one-way function. That's my analogous claim. And when I say it's hard to find a claw, I mean that if a computer, given this function, if he can find a claw, then he can break some underlying cryptographic assumption. In my case, the assumption will be learning with errors. So if a computer, whether classical or quantum, can find this claw, he can use his claw finding algorithm to break learning with errors. What that means is our assumption is that it is hard to find a claw, which is a pair of matching pre-images. That's the claw-free property. The final property is the trapdoor property. The trapdoor property says that there is a trapdoor, there exists a trapdoor, which allows for efficient inversion. So there's a trapdoor, there's an algorithm, which takes as input the trapdoor, the image y, and it can output both pre-images of y. Just to clarify, this might seem confusing because in the second property, I said it's hard to find a claw. The third property, I said, here's how you find a claw. The difference is the third property requires the trapdoor to find a claw. So the second property says if a computer, classical or quantum, does not have access to the trapdoor, then it is hard for that computer to find the claw. The third property says that if a classical computer has access to a trapdoor, that classical computer can find any claw. It can efficiently invert an image y and find the two corresponding pre-images. Okay, this definition is very important and I'll be using it for the rest of this talk. So are there any questions to clarify this definition?
Yes, there was just a question in the chat.
Great.
Wilfried, would you like to ask directly?
Yeah, so I'm wondering if there's a more precise way to say it's hard to find a claw. It seems a bit arbitrary. One could think of some hierarchy of quote unquote hardness, and I'm wondering if there's more you can say about that.
Okay, so let me just state it more precisely. If an algorithm can find a claw, meaning if there is an algorithm which can output a claw, then this algorithm can break learning with errors. So this algorithm can take as input a system of noisy linear equations and solve it. Does that address your question?
Yeah. So I'm wondering now, is it possible to compare two algorithms that can find a claw, but maybe the structure, the maps are different? Mm-hmm. And so one algorithm is actually better than another, even though both can find claws, because they find claws in different for different mappings.
Yeah, that's a reasonable question. So what happens is when I say if you find a claw, you can break learning with errors, I build an algorithm for learning with errors, which has this claw finding algorithm kind of as a box in the algorithm, as a subroutine. And so you're saying, okay, well, one subroutine is more efficient than the other. That just means that my overall LWE breaking algorithm will be more efficient in one case than the other. But either way, we're breaking learning with errors, but depending on what the subroutine does, the efficiency can vary.
All right, thanks.
Yeah.
I could just a follow-up question.
Yeah,
I guess when you say hard, you meant like there doesn't exist a polynomial time algorithm to find this claw, right?
Exactly.
You're talking about NP hardness, okay?
It's not NP hardness because it's just what you said. We don't believe there exists an efficient algorithm to solve it.
To solve it, okay.
Yeah.
Okay, thanks.
Yeah.
And I have another question. is this these properties all for a fixed given y, or for all possible images y that somebody might come up with?
For all possible images y.
Okay, thanks.
Yeah. Okay, great. Thank you for the questions. So let's continue. So we defined this claw-free function, and it has nice properties, and it's an interesting function. But why is it so great in the quantum? Yeah. Was there another question? No.
Yes,
okay.
please. I have a question.
Oh yeah, yeah.
Do you hear me?
Yes,
Yeah,
go ahead.
I can hear you.
Okay, thank you. So, according to the description of your meeting, I have a question. What should be the response if the information is a classical bit?
Sorry, I didn't follow
If
the question.
if your information is transmitted in classical bit, what should be the response of your machine?
I didn't follow the question. If anyone else did, then you.
I think maybe, so here, all of this, I mean, the x0 and the x1 is all classical, right? It's just some inputs to a function, is that right?
Exactly.
Yes.
Okay.
So,
Okay. Thank you.
yes. I
Yeah,
think
the
that might be
functions are
correct.
entirely classical, so it's classical cryptography.
Okay, classical. Thank you.
Thank you. Okay, so the function, that was a good question. The functions are entirely classical, but the hardness is quantum, meaning the functions are classical, but I'm saying even a quantum computer can't find a claw. Okay, great. So these functions are interesting. They have nice properties, but why are they so nice in the quantum setting? It turns out that a quantum computer can do something very strange with these functions. And here's what a quantum computer can do. A quantum computer can sample a random image y and create a uniform superposition over the corresponding claw. So he has a superposition, which is kind of in flux between the claw, the two members of the claw, x0 and x1. It is very easy for a quantum computer to do this. I probably will not get into it in this talk. I would like you to take it as an assumption that a quantum computer can very easily create this state. And the state is very interesting because I said that even a quantum computer cannot find a claw, yet the quantum computer is creating a superposition over a claw. So why is that not a contradiction? The reason it's not a contradiction is because, remember what I told you earlier, in order to actually gain information from a quantum state, we have to measure it. So these two members of the claw are in superposition, which means we don't actually have access to them. So we'd have to measure the state. And it turns out that when you measure the state, you can't actually extract the full claw because they're in superposition, but you can extract some information, which is not possible to obtain classically. And that's why it's interesting, because a quantum computer can create this state, and using the state, he can do something that is actually impossible to do classically. We can show that it's impossible to do classically. And this kind of thing is, so that means this function kind of draws a line between quantum computers and classical computers, and we can use this difference in ability to test quantum computers, because we know that classical computers can't do them. So over the next few slides, I'll clarify exactly what that means. But for now, I told you that, okay, he has this state, and it doesn't break the claw-free assumption. So let me tell you what that means by telling you what happens when we measure the state. So here's the state. Well, we can measure it. There are many different measurements in the quantum world, like you can measure it in many different bases. I'm only going to be dealing with two, and I'll tell you what happens in both cases. So one case is called the standard basis measurement. That's what I brought up earlier. And here, what would happen is the state will collapse to either 0x0 or 1x1, each with equal probability. That's not very interesting because I can actually do the same exact thing classically, because at this point, all the quantum computer has done is he's sampled a random pre-image image pair. So he's either sampled x0y or x1y. We can do that very easily by just sampling x at random and evaluating either f0 or f1. So this is not interesting. We can do all this classically. It gets interesting when we measure something in the Fourier basis. The Hadamard transform is the quantum Fourier transform. It's a reflection by pi by 8, and it's what creates quantum superpositions. This is really a very, very important quantum gate, and it's what makes quantum computations possible. So what it does is it maps 0 to a superposition over 0 and 1, and it maps 1 to a superposition over 0 and 1. There's a phase of -1. You don't have to think too much about this. We don't have to get into the technical details. Just understanding it at this very high level is enough. So if we do a Hadamard basis measurement on this entire state, I'm not going to work out the math, but what happens is the output is a string D, which satisfies this equation. So to break that down, x0 and x1 are bit strings. We're taking a bitwise XOR. Then we're taking the bitwise inner product mod 2. So by measuring in the Hadamard basis, the quantum computer can obtain a string D, which satisfies this equation, which is with respect to both members of the claw. This is the information that is classically impossible to obtain because it has to do with both members of the claw. And we can formalize this. We can actually say that if a classical machine can obtain this information, then a classical machine can break the claw-free property. And the way we formalize that is, I said, okay, there's this claw-free property. We can strengthen the claw-free property. The claw-free property said that it's hard to hold both x0 and x1. We can strengthen it to say that not only is it hard to hold both x0 and x1, it's hard to hold x0 and even a single bit of x1 at the same time, or vice versa. It's hard to hold x1 and even a single bit of x0. What that says is that if the classical computer holds x0, then the classical computer cannot produce this string D, because this string D would reveal a single bit of x1. So what we show is that before I said this trapdoor claw-free function is hard, assuming learning with errors. And we can actually show that not only is the claw-free property hard, this stronger property, this adaptive hardcore bit property, is also hard. If a classical computer can break that property, it can do the same thing. It can break learning with errors. And this was shown in joint work with Zvika Bekersky, Paul Cristiano, Umesh Vazirani, and Tomas Videk. Now, what I said so far, it went fast, but we're going to go through it all again. So what I said so far is that the quantum computer can create a state, which is a superposition over the claw, and he can use this state to produce this string D, which is classically impossible to produce. Therefore, this state differentiates classical and quantum computers and can therefore be used as a classical test to verify that a machine is actually quantum. So remember, our goal for this talk was to verify the output of a quantum computation. This is kind of an intermediate step where I'm not verifying the output, but I'm verifying that a machine is actually quantum. And I'll give you that full test in this talk. And it turns out that this test can be kind of used as a building block to build this more powerful protocol of actually verifying the output rather than just verifying quantumness. So the next thing I'm going to do is I'm going to go into this test for quantumness. I'll tell you exactly what it means and how to build it from trapdoor claw-free functions. Before that, are there any questions? Because I know I covered a lot in the last 2 slides.
So far, there are no questions in the chat, but yeah.
Yes, I have a question. So what is the real goal? The real goal is to actually prove that the computer is quantum, or to break the error testing at the end, the learning errors. What is the real goal?
The real goal is to actually prove that the output to a quantum computer is correct. And in this intermediate goal, I want to do what you said, prove that a computer is quantum. Breaking learning with errors is not a goal. We don't believe that quantum computers cannot break learning with errors. Instead, it's an assumption. I'm going to say I can classically test at quantum computers, assuming that quantum computers cannot break learning with errors.
All right, thanks.
Yeah.
I don't see any other questions at the moment.
Okay, thanks, Franca. I'll continue. So I kind of gave you the high-level notion of what a test for quantumness is, but let's actually write down what it is. So we still have this classical computer, which is represented by a laptop. Now the notion has slightly changed. Instead of verifying the output to a quantum computation, we want to verify that a machine is actually quantum. So this classical computer is interacting with some device, and this device says, yes, I'm a quantum machine, but this classical computer has no way of verifying it. So this is very relevant in this upcoming near-term development of quantum computers, because here, all these companies are saying, yes, we built quantum computers, but how do we know? How do we know they aren't just classical supercomputers, or how do we know that they're actually doing something quantum? This is what a test for quantumness is. So what we'll guarantee is that in this test, if the machine passes the test, so if the verifier or the classical laptop accepts, either the machine is a classical machine, which is taking exponentially long, so it's an inefficient classical machine, or it has to be quantum. So this first thing is basically saying either it's a classical machine, which is capable of breaking the cryptography, or if it can't break the cryptography, it has to be a quantum machine. There's no other option. This is a pretty powerful test, and it gives a protocol for something called verifiable quantum supremacy. So currently in the media, people are talking about quantum supremacy, which means they think they've built a device which surpasses the power of classical devices. So it's supreme, it's better than classical devices. The problem is what I mentioned very early on in the talk, where I said, we're building these devices and they're getting larger and larger. And once they get too large, we can't actually classically verify that these devices are quantum and that they're better than classical. And so what this protocol is saying is, here is an actual method of classically verifying quantum supremacy, classically verifying that a quantum device is better than classical. Because that's kind of, that seems contradictory, right? If a quantum device is better than a classical device, then how do we test it with a classical device? And this is giving a protocol for that. It's saying interaction makes that possible. Okay, so now we know what a test for quantumness is. Let's bring back the trapdoor claw-free functions and actually build this test. Here's how it goes. The verifier selects a trapdoor claw-free function pair F0 and F1. He selects that function pair along with the trapdoor. The verifier keeps the trapdoor to himself. He'll need it later on. And he sends F0 and F1 over to this computer, over to this device, which is claiming to be quantum. Then this device, which we'll call the prover, what he's supposed to do is create the superposition over the claw and report the corresponding random image Y. Of course, I have no idea what he's actually doing. I'm saying this is what an honest quantum machine would do in order to pass the test. Then the verifier chooses to test him at random. This is where the power of interaction comes in, because this device has no idea what this randomness will be. The verifier will send over a single bit, either 0 or 1. If the bit is 0, this is a pre-image test. The device is meant to send back either x0 or x1. This is easy. If the device was quantum and actually did things honestly, he would just have to measure his state in the standard basis, and it would collapse to either x0 or x1. If the verifier sent over the bit 1, he's asking for a string D, which we'll call an equation test. In this case, he expects the device to send back a string D, which satisfies this equation that we talked about earlier. Again, if the device was honest and actually created this superposition, all he has to do is measure it in this Hadamard Fourier basis, and he'll get the string D, which satisfies this equation. Finally, the verifier uses the trapdoor to check if the prover passes, because the verifier needs the trapdoor to look at Y, compute x0 and x1, and check that the prover's answers are actually correct, meaning it's either x0 or x1, or it's the string D, which satisfies this equation. This is the full test. So the test is actually quite simple given the definition of the TCF pair. Now I need to prove to you that this is actually a test for quantum supremacy. So that consists of two parts. The first is saying that an honest quantum computer can pass that test. I think I've already argued that. The second is saying that a classical computer cannot pass the test without breaking the underlying cryptography, which in this case is learning with errors. So what happens? Let's say a classical prover can pass the test. The problem is, in that case, that classical computers can be rewound. So what I could do is I could run this classical computer on the 0 query. Then the classical computer, since he passes, has to give me back x0 or x1. Then I could rewind him, and I could run him on the 1 query. Again, since he passes, now he has to give me this string D. That means the classical computer can hold both x0 or x1 and the string D, which reveals a single bit of the other preimage. So let's say he held x0 and a string D. Now he has x0 and a single bit of x1. This violates the adaptive hardcore bit property, which was the strengthened version of the claw-free property, thereby saying that if a classical machine can pass both tests, he can break learning with errors. This is a nice argument, it's very neat, but how come it didn't apply to quantum computers? How come a quantum computer could pass both tests without breaking the cryptography? Now, that is because of a fundamental property of quantum machines. Quantum machines cannot be rewound. Once we measure a quantum state, there is no way of going back. So if a quantum computer measures the state and gets either x0 or x1, at that point, the state has collapsed and he cannot reconstruct the superposition over 0x0 and x1x1. That's just a fundamental property of how quantum computers behave. So that was the key difference here. This is what makes it possible to test quantum machines. Quantum machines can use a superposition to pass this test. If a classical machine passes the test, it can be rewound and break the cryptography. So what I've said so far is that this test, if a machine can perform both of these tests, like the 0-1 test with a pre-image or the equation, it cannot be classical. That gives a protocol for classically verifiable quantum supremacy, meaning a protocol to classically verify that a machine is actually quantum. It turns out that this structure with trapdoor claw-free functions is useful for a variety of different tasks. The other one is something called randomness generation. So what I said earlier was that when the quantum computer measures the state, it collapses uniformly at random to either 0x0 or 1x1. This property means that quantum computers, when they measure, are actually generating true randomness. So a central question in quantum cryptography is, can we harness this true randomness? So if we have a quantum computer, can I ask him to measure, give me the outputs, and then can I use this as true randomness? True randomness is very important in quantum computing because we use it in cryptography or in algorithms, and there is no way of classically generating it. So the question is, if a quantum computer says it's producing randomness, can we verify that that was actually true randomness? That quantum computer did actually obtain that measurement by obtain that randomness by measuring a quantum state. This protocol gives us a way of generating certified randomness, because what it says is that if a machine passes this protocol, it had to be generating randomness, because if it was deterministic machines can always be rewound. So then we can rewind the machine and get that same contradiction where it obtains both x0 and a string d. That means if a machine performs both tasks, it cannot be deterministic, which gives us a protocol for certified randomness generation. The final thing is totally different than what we've talked about. There's something called homomorphic encryption. Homomorphic encryption is essentially blind quantum computing on the cloud. So in this setting, let's say you have a classical computer. There's a quantum computer on the cloud. You have access to it and it can perform very powerful quantum computations. So you have some data and you want to run some powerful computation on it, and you'd like to delegate it to the quantum computation. Unfortunately, maybe the machine that runs the quantum computer, you don't quite trust it, you don't want it to have your data. So is there a way of encrypting your data, sending it over to the quantum computer? The quantum computer should be able to perform the full quantum computation on top of your classically encrypted data and send back the classically encrypted result. Then all you have to do is decrypt it. You get your final output. You have the guarantee that the quantum computer learned nothing because he computed on encrypted data the whole time. That's called homomorphic encryption. And it turns out that this structure can be used to build a homomorphic encryption, which allows classical computers to privately delegate their data to quantum computers. And finally, this structure is also used to classically verify quantum computers. So I said this structure is used to verify quantumness, but it can actually be used to not only verify quantumness, to actually verify that the output of a quantum computation is correct. Unfortunately, I don't have time to get into that in this talk, but let me wrap up what I've said about verification, and then I'll give you a couple open questions. So I started this talk by asking whether quantum computations can be verified classically. And my main point was that interaction and cryptography can be used to allow the verifier to gain leverage over the quantum computer. So they started off with this power imbalance where the verifier was much weaker than the quantum computer, but interaction just kind of allowed the verifier to put a leash on the quantum computer and control its behavior. The cryptography that I used was called Trapdoor Property functions. These were built using the assumption that quantum computers cannot break the learning with errors problem. And I showed that they could be used to build a test that a machine is actually quantum. And finally, I didn't prove this, but I told you that we could use this structure to not only verify that a machine is quantum, but actually verify that the output to this quantum computation is correct. And all of this together tells us that classical verification of quantum computations is possible, assuming that quantum computers cannot break learning with errors. So that's what I've told you so far in this talk. Let me just end with a couple of open questions. So I gave you this verifiable supremacy test, and I said one of the key applications was to use it on near-term quantum devices, meaning these small quantum devices which are just getting past the threshold of classical supercomputing power. The problem is that the protocol that I gave you, it's classically verifiable, but it's currently not efficient to run on these very small quantum computers because it requires more qubits. So that's one question. Can we actually make it efficient enough? Because the current status in the field is that the existing tests are efficient to run on these near-term devices, but they require actual simulation. They require classical supercomputers to verify. So once we pass this threshold, when we can't simulate anymore, then these tests can't be verified. So the test that I gave you has the pro that it can be verified, but it has the con that it's not as efficient as these existing tests. Okay, and the final open question, oh, sorry. So the last thing is the reason that these tests are not efficient is because it requires application of this trapdoor claw-free function, which is built from learning with errors. And it turns out that application of those functions is computationally, it's not cheap. It does take some computational work. So to improve this, one way of doing it is to build it from a more efficient function rather than learning with errors. That's one possibility. So my favorite open question is whether we can classically verify quantum computers without assumptions. So in this whole talk, I said, I'm assuming that the quantum computer cannot break learning with errors. Can I take away that assumption? Can I say that even if a quantum computer is all powerful, I cannot assume any upper bounds? That there is some method for a classical verifier to catch him if he lies. So even this all-powerful quantum computer cannot trick this verification protocol. This is a major open question. There has been very little progress on it, but happily there are also no impossibility results. I like this question because it links to complexity theory. Like everything I just told you links to cryptography, but this is a purely complexity theoretic question. And it's quite nice because it allows you to explore kind of the power and limitations of quantum computers and how classical computers can actually control quantum computers through interaction. So that's all. That's the end of my talk. Thank you so much for listening.
Thank you, Urmila. Thank you very much. Yeah, I would like to open the floor for questions or comments and thoughts.
Yeah, can I ask a question?
Yeah,
go ahead.
Thank you, Urmila, for a wonderful talk. The last open problem that you wrote is very appealing to me, and I wanted to know whether there are any implications either way for non-complexity classes, for whether the answer is yes, it's possible to do without assumption, or no, it's not possible to do without assumptions.
Yeah, that's a great question. And the nice thing is that there are no implications, which that's what I meant when I said there are no impossibility results. There's nothing saying that, you know, if we have this result, then we have this horrible complexity collapse. We have no reason to believe that this isn't possible. There are some weak impossibility, meaning like there's something saying if you can verify in a constant number of rounds, then you get a complexity collapse. So we don't believe that this is possible in a constant number of rounds, but there's nothing to say that it's not possible with greater number of rounds.
Thank you. And follow-up question is, this learning with errors, is it in your proofs the minimal, the easiest problem we can consider in order to establish this separation, this verifiability?
Easiest in what way?
In the sense of hardness. So cryptographic assumptions. Is it the least of the cryptographic assumptions we can make in order to get the result?
Oh, that's a really good question. So there are better assumptions, meaning assumptions that are more widely believed. Like, for example, one assumption is the existence of one-way functions. That is a weaker assumption than this, and we don't know how to build it. And there is nothing to indicate that it's impossible. It's just that this is a new area, so people haven't explored all the different possibilities. So that's a really good direction to think about.
Thank you very much.
Yeah.
I have a follow-up question on this, actually. Just right on that point. So you were focusing on the learning with errors. Does the proof of the result, as it is right now, rely on the specific choice of the learning with errors? Or let's say if tomorrow we found another problem that quantum computers cannot break, would the same arguments apply immediately?
Okay, that's also a really good question. So we did try to isolate it. So what we did was we gave a definition of these trapdoor claw-free function pairs. And in this definition, there were all these properties. And we said, if these properties are satisfied, then you get these verification results. Then we showed that you can satisfy all these properties using learning with errors. So if you can take any other cryptographic assumption and build these functions which satisfy these properties, then you're good, because our result just plugs in on top. The problem is that these properties, more specifically that adaptive hardcore bit property, where it's hard to hold even a single bit of the other claw, that is hard. It's I don't know of any other assumptions for which such a strong property holds. So the answer is that if you find an assumption that satisfies all these properties, you're good. From what I know, people don't know of other things that satisfy those properties. But again, that it could purely be a result of a lack of study, because this adaptive hardcore bit property was never used before this work. Because it's this very weird thing that was useful in our setting, but no one else cared about.
Oh wow, that's fascinating.
Yeah, it's weird. Like there are all these weird properties that happen to be satisfied, but no one cared about before. So.
And there's some thank yous for the presentation in the chat also. I have one other follow-up question.
Yeah.
So something that I was very amazed by when I listened to you is that this way of using classical ideas to verify quantum computing, so that by itself is something new here in this approach. So how did nobody think about this before? I mean, I'm completely outside the area, so I don't try to ask a condescending question, but
no, it's okay. So this question has been very well studied since it was asked. I think that was like in 2004, 2008. And how did no one think of this before? I guess the problem was, so we all knew that there was classical cryptography that quantum computers could not break. But what was very hard was, how do you use this cryptography to actually control the behavior of the quantum machine? That's the hard part, right? Like, sure, the quantum computer cannot break it, but just the fact that he can't break it doesn't mean that he's going to give me the correct output. How do you link that? How do you say he only gives me the correct output? He only gives me the incorrect output if he's breaking the cryptography. So that was just kind of a very... So just to give you some context, all of the previous results, they went in two different models. One, the verifier needed a small quantum computer. The small quantum computer was used to send over quantum bits to the prover, and these quantum bits had some secret structure that the prover couldn't figure out, and so the prover had to behave honestly, otherwise he'd break the structure. So this kind of thing, like the only way we knew how to control the power of a quantum computer was by starting with some quantumness and using this to kind of leash the quantum computer. So we didn't know how to tie the hands of a quantum computer only using classical ideas.
Oh, wow. So the analogy with the tree would be that one can figure out this idea of sending the person that can count the leaves on the tree away, pluck some leaves off, and then call the person back. So that idea, that procedure, would be the analogy of this.
I didn't get analogy of what?
a new approach to use interaction to check on a quantum computer without having the same capabilities as the quantum computer.
That is what we're doing. I'm not quite getting the analogy with the leaves.
That the protocol that you suggest corresponds in the analogy to the idea to plug off some leaves and just count how many leaves you plugged off and then send again the person to count the leaves. I mean, maybe it's going a bit too far.
No, I mean, that is it.
Okay.
That was the part of the protocol that gave the verifier power. So yes, we need like something analogous to that to kind of control the, yeah. That's
Okay.
a good question. I just didn't have a good answer, like as to why no one did. Yeah.
Yeah, any other questions? Okay. So in that case, I would like to thank you again, Urmila. I learned a lot again, even though I've seen you talk about this before. So I hope also I'm sure other people took away some new exciting insights. I know today was a bit of an unusual time. So next time we're planning to go back to our usual time slot. Yeah, so if you want to stay on the call, I will stay a bit longer. But yeah, thank you very much.
Thank you.
Thank you, Urmila. Yeah, nice talk.
Thank you.
Good.
Yeah,